Moving charges and magnetism, force between two parallel currents. So here we take two conductors A and B, and these conductors have been placed parallel to each other. The directions of currents IA and IB respectively are also parallel to each other in the two conductors, and the separation between them be small d. Now, we can easily find the magnetic field of conductor A due to current IA at any point on conductor B, because it will be same at all points since the two conductors are parallel, and we can do this by using Ampere's circuitry law, which has already been explained in previous portions. So according to Ampere's circuitry law, this magnetic field of conductor A at any point on conductor B is mu naught Ia upon 2 pi d, where d is the distance between the two. This we have written the formula in accordance with Ampere's circuitry law. You can check it out. Now, the direction of this magnetic field BA, which is field of conductor A at B, it can be given by right hand thumb rule. Right hand thumb rule is also explained in previous videos. The link is given in the I box or I button. You can check it out there. So the direction as given by right hand thumb rule is downwards, vertically downwards, if the conductors are placed horizontally. So you can see this is the direction of magnetic field BA here. It is vertically downwards. So this is how we find the magnetic field. Now we take a small portion or some part of the conductor A having a length capital L. So we wish to determine the force on this length L of the conductor due to the magnetic field BA, which we have already derived. So this force is given by ILB sine theta. Since we are familiar with force on a current carrying conductor placed in a magnetic field, it is given by ILB sine theta. ILB sine theta. So likewise, and here since the direction of current is horizontal while direction of magnetic field is vertical, so the angle theta is 90 degree here. So sine theta automatically becomes 1. Sine 90 is 1. So sine theta becomes 1. So what remains is only ILB, and sine 90 is 1. So that's why we can simply write from this discussion, we can simply write the amount of force acting on this length L as ILB, because sine theta has been put as 1 equal to 1. So ILB. Now here, since the current of conductor B is concerned, that's why current IB has been taken, and magnetic field of A is under consideration, that's why BA. So this is how we get the force on length L. And when I substitute the value of magnetic field BA over here in this formula, then we get the overall expression like this. It is the expression for force on length L of the conductor B. And the direction of this force is given by Fleming's left hand rule. Again, Fleming's left hand rule has been explained in the previous video. The link is in the I button. You can go and check it out. So the direction of this force as given by Fleming's left hand rule is found to be towards the conductor A. So we see that the force on B is acting such that it is pulling it towards A. So it's an attractive force. We can easily say it is an attractive force. Similarly, there will be a force on conductor A due to B, which can be named as FAB. Okay, and this force will be such that it will pull A towards B, something like this, and it will be named as FAB. All right. So we can easily tell from this discussion that the two forces FAB and FBA are equal and opposite to each other. So the two forces are FAB and FBA, and FBA is minus FAB. So our conclusion is that two parallel currents will attract each other while anti-parallel currents will repel each other. If these two currents would have been anti-parallel at angle of 180 degree, then they would exert repulsive forces. But here, since they are parallel, so they are attracting each other. So this is the conclusion. Now, we can also find the force per unit length of this conductor. This force that we have determined, this expression, it was for length L. Now, easily by dividing this expression with L, we can find the force per unit length. So just L gets cancelled and this force per unit length is represented by small f BA, and similarly small f AB can also be determined. So this is the force per unit length. From the above expression of force, we can also define ampere. So the definition of ampere is like this. The ampere is the value of that steady current which, when passing through each of these two conductors, of negligible cross section and such that they are placed 1 meter apart in vacuum, then it would produce a force per unit length of 2 into 10 raised to the minus 7 Newton per meter. So I would explain this. So we have just now derived the expression for FBA or FAB for that matter, and it is mu naught upon 2 pi IAIB into IAIB upon D, right? Mu naught IAIB upon 2 pi D, something like this, the expression that we derived in the previous part. So if we take the two currents IA and IB equal to 1 ampere each, we are just putting the values each of 1 ampere, so it becomes 1 into 1 upon, we are placing them 1 meter apart as mentioned in the definition. So each is having the current is 1 ampere, we are defining it. So each is having 1 ampere current and placed, two of them are placed 1 meter apart. Then the force per unit length comes out to be mu naught upon 2 pi. We have just substituted the values of IA, IB and D as 1 numerical value. So it comes out to be mu naught upon 2 pi. And what is the value of mu naught upon 2 pi? It is 2 into 10 raised to the power minus 7. So we see that the force per unit length is 2 into 10 raised to the power minus 7 Newton per meter. So this helps us to define 1 ampere. So from now on, you will be using this definition of ampere or 1 ampere. In the same way, we can use this expression to define Coulomb also. So the definition of Coulomb is easily given by the formula that when a current of 1 ampere is passing in a conductor, then the amount of charge that flows through it in 1 second is 1 Coulomb charge, because we know that I is Q by T, right? I is charge flowing per unit time. So if current is 1 ampere and time is 1 second, that means 1 ampere current is flowing in 1 second time. That means how much charge is flowing here? It comes out to be, Q comes out to be 1 Coulomb. So this is a definition of Coulomb as well. In this way, we can define the Coulomb as well as the ampere from the above discussion. Thank you. Like, share and subscribe to the physics side for more interesting and informative videos. Also, the practical side is now the physics side.